chemistry too. And so the next reaction I want to look at is this: potassium sulfide and acetic acid. And so what's the formula for potassium sulfide? K2S. So this one we'll go through here. K2S, potassium sulfide. What's the formula for acetic acid? Good. HC2H3O2. HC2H3O2. Last semester I noticed some people writing it like this: H4C2O2, which actually drove me crazy because I can't stand it written like this. Do you know why? Why? Because you're losing some information. If you write it like this, yes, there are 4 hydrogens, but these 4 hydrogens aren't all the same. And to group them all together like this, it makes it look like they're the same. So we're losing some structural information. Really, there are 3 hydrogens that are similar, like this. And then there's 1 hydrogen that's different. That's this. And so this turns out to have only 1 acidic hydrogen, and these 3 here are what we call non-acidic hydrogens. And so this is separating out the acidic hydrogen from the non-acidic hydrogens, which is useful. This is monoprotic acid. This is not a tetraprotic acid. What's even better is something that retains more of the structure. This is called a condensed structural formula. And so are you guys familiar with this way of writing acetic acid? This is very common. And so CH3COOH shows it as this. It's just a condensation. And so if we have not just the composition is important, but also the structure is important too. And so we want to retain as much structural information as we can. So this is probably the most compact way of writing it. The best way of writing it is maybe a full Lewis structure like this. Maybe a 3-dimensional structure would be even better. Showing what type of carbon is this? Is that a sp3 carbon or sp2 carbon or sp carbon? What is that? That's sp3. This is a sp2 carbon. This is tetrahedral. This is trigonal planar. And so we want some structural information there. And it gives us some additional insight into the properties. But this is fine too, HC2H3O2. And so this is just a standard AB plus CD type of metathesis reaction. What forms? Potassium acetate and hydrogen sulfide, H2S. Is there any driving force for this reaction? Yeah. Hydrogen sulfide isn't very soluble in water. Do you guys recall the definition of solubility? There are 2 definitions for solubility. One definition is it soluble or not soluble? That's qualitative. The other definition of solubility is the maximum amount of solute that will dissolve in a given amount of solvent. And so the solubility of hydrogen sulfide is only 0.1 molar. That is, the maximum amount of H2S we can put in water is 0.1 moles per liter. It's not very much. And so once we exceed 0.1 molar, the rest will bubble out. And so we could either use AT or gas, but we have plenty. And so we'll get some H2S in solution, but most of it will bubble out. And so we have gas formation here. Are there any other driving forces that you might see in this? Yes, weaker acid. And so we're going from a stronger acid. What's a stronger acid? Well, acetic acid, to a weaker acid. What's a weaker acid? Yeah, hydrogen sulfide. This is a weaker acid. So stronger acid to weaker acid. And so this is a driving force. For our acids chart, again, you'll get familiar with this on Piazza. I posted these, so this is up here. You can see hydrogen sulfide is a stronger acid. Oops, not hydrogen sulfide. What? Acetic acid is a stronger acid than hydrogen sulfide. So do you see acetic acid on the chart? Yeah. Acetic acid is stronger than hydrogen sulfide. And so we're going from stronger acid to weaker acid. That's going to drive this reaction. And so the next thing to do is to balance this. Let's go ahead and do that. Balancing this, we'll need 2 acetic acids and 2 potassium acetate. What about potassium acetate? Will that precipitate out? Yes or no? Yes? What's the rule for potassium salt? Potassium salts are all soluble. So will it precipitate out? No. So this is it. So this will be our conventional equation. Then we go to the ionic equation. In the ionic equation, we dissociate the strong electrolytes. So is potassium sulfide a strong electrolyte? Yes. What are the strong electrolytes? There are 3 things that are strong electrolytes. Strong acids, strong bases, and the soluble salts, which are ionic compounds. Soluble ionic compounds. So potassium sulfide, soluble, group 1s. And so we dissociate into what? 2 potassiums and 1 sulfide. 2 potassiums and 1 sulfide. And so I need to stop for a moment. I'm going to put a little asterisk here next to sulfide. The reason I put that there. Okay, how about acetic acid? Is acetic acid a strong acid? Do you guys know the 7 strong acids, the common ones? No, it's not. The 7 are actually 6 of the 7 are here. The common ones. And we have that. And so acetic acid is not one of them, therefore it's likely to be weak, right? And so weak acids, do we dissociate those? No. So we leave this alone. Major species will be acetic acid molecules. Potassium acetate, dissociate that. Soluble salt, yes, is dissociated. So 2 potassiums and 2 acetates. Don't forget to balance this. It's going to be 2 and 2. H2S, do we dissociate that? No. H2S is a weak acid. So that does not dissociate. We leave it alone. All right, so you guys know the 7 strong acids, but do you know what the strong bases are? Can you tell me what the strong bases are? How many strong bases are there? Are there 7 strong bases or 6 strong bases? What are the 6 strong bases? Sodium hydroxide, 1. Lithium hydroxide, 2. Potassium hydroxide, 3. Rubidium hydroxide, 4. Magnesium hydroxide, is that a strong base? Magnesium hydroxide is considered a weak base. It's not considered a strong base. Why is magnesium hydroxide not a strong base? For example, think about this. You can drink magnesium hydroxide. Have you heard milk of magnesia? It's a slurry of magnesium hydroxide. It's like a paste because it's not soluble. You can drink this stuff it's an antacid. But would you, let's say you ran out of magnesium hydroxide, would you grab a bottle of sodium hydroxide off the shelf and drink that? You know, a little upset stomach, drink some sodium hydroxide. Why is it okay to drink magnesium hydroxide, but and it won't kill you, but sodium hydroxide, you'll die if you drink that stuff? It's drain cleaner. Why? Why is that? Well, because sodium hydroxide is a strong base, magnesium hydroxide is a weak base. So why is it strong? Why is it weak? It's not the activity series. Activity series has to do with redox, not acid base. We have to keep it separate. That's why I separate the reactions in this way. Activity series, redox. Well, the reason is you should know the strong bases. What are the strong bases? You know, the strong bases are simple. The strong bases are the soluble hydroxides. What are the soluble hydroxides? Group 1, ammonium and calcium, strontium, barium. Everything else is not considered a strong base. So for example, if you had iron 3 hydroxide, strong base? No. Iron 3 hydroxide is not considered a strong base because it's an insoluble hydroxide. And so however many there are, I don't know, you could count them, but I don't bother counting them because I know it's group 1 and ammonium and calcium, strontium, and barium, right? It's more than 6. Is that it? Are there other strong bases in addition to that? Are there? No? What do you think? How about Jasmine? Are there other strong bases other than the soluble hydroxides? No? Just the soluble hydroxide?
I mean, they are, but aren't they equal to value?
Oh, I mean, okay, so there are, but they're equal in value?
Yeah.
Okay. Yeah, there are. There are other strong bases other than hydroxide, right? And so if you look at the chart in our classroom, what's the strongest base here? It's not hydroxide. The strongest base in the chart in our classroom is what's this called? This is not ammonia. Ammonia is actually a moderate base. That's ammonia. NH2 minus is called amide. Amide. So if you don't know this, amide is the strongest base on this acid base chart. Amide. And so what are the strong bases? The strong bases are all soluble hydroxides, all soluble amides, because we need it to dissolve in water and dissociate. And not only that, what's this? What's this ion called? Not peroxide. Peroxide is O2 minus. This is oxide. All soluble oxides are strong bases. What are the soluble oxides? What would you guess? The soluble oxides are. For example, iron 3 oxide. Do you think it's soluble? Iron 3 oxide. Soluble? Rust. Can you just wash rust off? It'll dissolve? No. It's insoluble. And so what are the soluble oxides? Group 1, ammonium. Group 1 and ammonium. Those are the soluble oxides. Well, that's on that chart. What about the chart I gave you? On the chart I gave you, amide is not the strongest. Actually, the chart I gave you has more recent data. This chart has old data. In fact, this green line I drew in, because this is wrong, sulfide is stronger than hydroxide. even though this chart was published in 1998, they never updated it since the 60s or the 70s. So, which is too bad. This chart, though, is more up to date, and it shows it's in this order. Amide's here. So hydroxide. Oh, there's also, what are these? Sulfides. And so the reason I brought up sulfide is, when you look at something like this, do you see strong base projecting? One of the chemical properties of sulfide is it's a powerful base, even stronger than hydroxide. Stronger than hydroxide. And so, you know, when I see something, this is why I put an asterisk there, because I know it's quite reactive. Strong bases are strong electrolytes. Oh, actually, we'll continue down. So memorize these. Well, you don't have to memorize. You see this enough that you just remember it. Hydroxides, sulfides, amides, oxides, hydrides. What do you think this is called? Methides. Methide or methide is a powerful base. What's the most powerful base on this chart? Methide. This would be rare. And so you got to remember these. Well, what's special about strong bases? Well, when we're dealing with ionic equations, we look for the strong electrolytes, right? Because the strong electrolytes, we need to dissociate the strong electrolytes. Well, sulfide pops up. Sulfide is a strong base. Strong bases are strong electrolytes. Strong electrolytes do what? Dissociate pretty much completely, right? But I have to start training you for something. Strong bases do not dissociate, just like weak bases. Do you know what weak bases do? Weak bases do not dissociate. Weak bases do what? Weak bases do what? Like ammonia. Ammonia does not dissociate. Remember that yesterday? Ammonia does what? Hydrolyze, right? Bases do not dissociate. Bases hydrolyze. Because what would you dissociate sulfide into? Sulfide's a strong base. What does it dissociate into? Tell me. What are you going to dissociate sulfide into? Protons, neutrons, and electrons? Is that it? No. Bases do not dissociate. Bases hydrolyze. And so if we have a strong base here, the reason why I wrote an asterisk is this. When you put a strong base in water, it's going to hydrolyze, right? It's going to hydrolyze. And so what that means is this. Sulfide, you know, sulfide does not exist in water. Sulfide cannot exist in water. You know why? Because it's a powerful base. And the powerful bases are going to hydrolyze close to 100% to form this. And so sulfide's going to attack water to form HS minus and hydroxide. And so if I had any sulfide in the water, the sulfide gets converted to HS minus and hydroxide. In fact, all of these bases here, all these bases here hydrolyze water pretty much 100%. And when they hydrolyze water, do you know what it forms? A base is a proton acceptor. It accepts a proton from water to form hydroxide. You see that? And so what happens is all these bases will react with water. And so if I tried, let's say I tried to make a 1 molar methide solution. If I tried to make a 1 molar methide solution, I'd be unsuccessful. Because the methide would hydrolyze water to form, instead of ending up with 1 molar methide, I'd end up with 1 molar hydroxide. Just like if I tried to make a 1 molar hydride solution, I'd end up with 1 molar hydroxide. All these are going to form, actually oxide's tricky because I'd end up with 2 molar, but skip that. Amide, I'm going to end up with hydroxide. And so all these hydrolyze water to produce hydroxide. Therefore, the strongest base that can exist stably in water is hydroxide. Do you see this is bordered off? The reason this is bordered off is because hydroxide is the strongest base that can exist in water stably. And all these bases are going to react with water to produce hydroxide. They all produce the same product. And therefore, as Jasmine was saying, they're all what did you say? They're all the same?
Yeah,
They're equal. Have you heard that? They're equal strength in water. Do you know what that effect is called? The leveling effect. This is the leveling effect of strong bases. The strong bases are all going to produce hydroxide. Therefore, they're all on the same level. You know, it's just this. If you have methide is more aggressive, but it produces the same product. You know, so it'll react more violently than sulfide. But in the end, after that initial reaction, we end up with the same thing. This is the same as acid. What's the strongest acid that can exist stably in water? Hydronium. And so if you try to get, what's this? Perchloric acid. You try to make 1 molar perchloric acid, you'd end up with 1 molar hydronium because the perchloric acid will attack water 100% or dissociate and form H+, right? And so let's say perchloric is a stronger acid than hydrochloric. But in water, is there going to be any difference? No, perchloric will react more violently, more quickly, but in the end, they produce the same amount of hydronium. So 1 molar perchloric, 1 molar HCl produce 1 molar hydronium and 1 molar hydronium. They're the same. That's a leveling effect, right? And so this is why, even though, let's say, HCl is a stronger acid than HNO3 in this, they're the same in water. And therefore, we should know something about this. Sulfide is too strong of a base to exist stably in water. And so this is actually wrong, because we wouldn't expect sulfide to exist in water. It should react with the water immediately to produce HS minus and OH minus. That's tricky because, you know, there's some acid-base chemistry happening in addition to this metathesis. Actually, there's, even with the metathesis, there's acid-base. But you know what? We're going to we could fix it, right? But maybe we'll just leave it because the end result is going to be the same. The HS minus that we produce here is plenty powerful enough of a base to strip another proton off acetic acid, and we end up with H2S. Here. So let's get rid of the spectators. We end up with S2 minus asterisk plus 2 acetic acids, 2 acetates, and an H2S. And so even if we replaced it, we'd end up with kind of the same thing happening. But we should be aware of that. And we should start recognizing strong acids and strong bases. Strong acids, we know easily what to do. We just dissociate them. But strong bases, you probably aren't familiar with what to do, right? And so strong bases, we got to hydrolyze them. All right, there's a couple of other examples in here you can work through at home. So let's move on to part 2. Part 2, we're going to look at acid-base reactions now. We see Arrhenius, Brunson, Lowry, Lewis. What are these? What are these three? Yes. But they're also what? When you look at those three things, what do they have in common?
They're all acid-base reactions at the different times.
Yeah. So one way of thinking about these, Arrhenius predates all these. Arrhenius comes along and sees acid. This is what he calls an acid. This is what he calls a base. So what these three are, these are three definitions of what an acid and base is, an acid-base reaction is. So Arrhenius comes along and says an acid is H plus AQ, base is OH minus AQ. But Bronsted and Lowry say there are many more acids that don't fit the Arrhenius definition. And so Bronsted opened up the definition to include more acids and more bases. And then Lewis comes along and said, oh, Bronsted-Lowry missed some acids and bases. And he came up with an even more general definition of what an acid and a base is. And so Lewis, nobody's come along and said, oh, there are some acids and bases Lewis missed. And so Lewis is the most general definition. And so what that means is we only need one definition. We need the most general definition that encompasses all acids and bases. So we should just stick with Lewis, get rid of number 1 and get rid of number 2, right? But we don't. We'll get rid of number 1. We don't need number 1. But we're going to keep number 2. Why?
Let's be safe.
No. Because Lewis will get all of them. It's not to be safe. If we just stuck with number 2 and eliminated number 3, then we're not safe. We could miss some.
No, for simplicity's sake.
Oh, for simplicity's sake, yes. Yeah, sorry, I thought you said to be safe. Yeah, you're right. For simplicity, Bronsted-Lowry are easy. Lewis are hard. And therefore, if it fits the Bronsted-Lowry definition, great, because you're going to have a much easier time. A much easier time because Bronsted-Lowry is like this. Over here, sulfide's the base, water's the acid. Water donates a proton, sulfide gains a proton. So it's simple. That's Bronsted-Lowry. And so we're going to get rid of the definition 1, keep definition 2, and 3. So let's take a look at Bronsted-Lowry acid-base reactions first. In Bronsted-Lowry, we just transfer 1 proton from the acid to the base. In the last one, how many protons did we transfer? Well, sulfide is what we call a dibasic base. It can accept 2 protons. And so we actually transferred 2 protons from 2 acetic acids, 1 from each. But when we do Bronsted-Lowry acid-base reactions, we only do 1 proton at a time. And then we determine if there's a driving force present, and then we look at further reaction occurs. That is, maybe it's a diprotic, maybe a triprotic, maybe there's further reaction. The method for dealing with Bronsted acid-base reactions is to inventory the solution. Inventory is just to use solubility and electrolyte properties to determine what the major species in solution is. And then we determine the strongest acid present and the strongest base present. And then we transfer a single proton from the acid to the base. We pick the strongest because the strongest have the highest probability of reacting. The weaker ones are going to have a lower probability, so we don't have to consider those. We just look at the most probable reaction. But even though we have the most probable reaction, there still might not be a reaction if there's no driving force. We've got to determine if the driving force is present. And then, it could be multiprotic, so we got to repeat this process to see if further reaction occurs. And so let's look at an example of Bronsted acid-base. So we're going to look at phosphoric acid and aqueous sodium hydroxide. We're going to do this using the metathesis approach and the Bronsted acid-base approach. So let's take a look at this. What's the formula for phosphoric acid? Okay, H3PO4. Phosphoric acid is a strong acid? Hmm? No. It's a weak acid, but it's borderline strong.
H3PO4, sodium hydroxide, NaOH.
Sodium hydroxide is a strong base? Yeah, it sure is. Strong base. But hydroxide exists stably in water, so we don't have to worry about what I was talking about with sulfides, right? So we're okay.
If we do this metathesis, in metathesis we react to completion.
That is, what am I going to form here? Well, phosphoric acid is a tricrotic acid, right? And so I'm going to neutralize all 3 protons. And I'm going to form what?
Well, AB plus CD gives water and
Sodium phosphate. What's the formula for sodium phosphate? Na3PO4.
Is there a driving force for this? Yeah, stronger acid, phosphoric to weaker acid. What's the weaker acid? Water.
Water is interesting because water is actually an amphoteric species. And so it could go either way, but in this case, that would be the weaker acid. Why is it the weaker acid? Well, it's actually the only acid over there.
And so there's a driving force for this. We just need to balance it. We'll need 3 sodium hydroxides, 3 waters. Water is a liquid. I'll write that here.
AQ I omit. It gets tiring to write aqueous. And so if you see it blank, that means aqueous. But if this were blank, then I'd mark you wrong, because water is not aqueous. Water is a liquid. So you could do the same.
All right, etc. We do the ionic equation. And we know phosphoric acid is a weak acid, so do we ionize it? No, we leave it alone.
Sodium hydroxide, that's a strong base, isn't it? Do we ionize it? Do we ionize strong bases? We hydrolyze. So how do we hydrolyze sodium hydroxide? Sodium hydroxide is tricky. Hydroxide is a strong base, right? Sodium hydroxide is what we call a soluble salt. And so soluble salts we ionize, so it's going to form 3 sodiums and 3 hydroxides. Now the hydroxide itself is a strong base. Now with a strong base like hydroxide, do we ionize it? Hydroxide is a strong base. Do we ionize it? No, we hydrolyze it. So hydroxide plus water produces what? We could see. Hydroxide plus water produces... No. Hydroxide's the base. Water's the acid. Proton is donated from the acid to the base. It forms H2O and hydroxide. Do you see that? So do we have to worry about hydrolyzing hydroxide? No, it'll exist in water. It's fine. If it reacts with water, it's just going to produce the same thing. Right?
And so when I ionize this, I'm treating it as a soluble salt, not a strong base. Once I've ionized it, then the hydroxide's a strong base.
Well, anyway, the H3PO4 stays as is.
And then we continue, etc. This is metathesis.
If I were to do this reaction using the Bronsted acid-base method, we approach it differently. First, we inventory the solution. And so what do I expect to find in solution?
Well, I expect to find phosphoric acid molecules. It's weak, so it doesn't ionize much. I expect to find sodium ions, right? I expect to find hydroxide ions. Right? I expect to find water, show liquid.
Okay, so let's go through this next. We determine the acids. There's phosphoric acid's an acid, right? Sodium ions, are those an acid? In the Bronsted definition, acids are proton donors. Is sodium ion a proton donor? Has an H plus it can give? No. Is it a proton acceptor? Like sodium plus H plus makes NaH2 plus, NaH2 plus? Does that sound good? No. And so we call this neutral. Neither acidic nor basic. Hydroxide. Hydroxide's a base. It's a strong base, right? But hydroxide is very tricky. Because not only is hydroxide a base, it could potentially be an acid. Did you know hydroxide could be an acid? It's shown here. Here's hydroxide, the acid. If hydroxide donates a proton, what does it form? Oxide. Are you guys familiar with the conjugate relationship? And so the conjugate base of hydroxide is oxide. Do you know the conjugate relationship is this? If the species is strong, then its conjugate will be weak. If the species is weak, its conjugate will be strong. That makes sense. And so is hydroxide a good acid? No. It's a very bad acid because oxide's a powerful base. Oxide wants the proton, and therefore if oxide has the proton, it's not going to let it go. And so in this case, it's an awful acid. It's one of the worst acids. It's like methane. You know, is methane good at neutralizing sodium hydroxide bases? Would you bubble methane gas and neutralize? No. Methane is not good at doing that, and therefore hydroxide is not a very good acid, but it could potentially react as an acid, therefore we should consider it. And so when I have hydroxide here, I consider it amphoteric. It's heavily biased towards one way. It's heavily biased towards base behavior, but it could also be an acid. And acid and base behavior depend on what you react it with, right? All of a sudden you have hydroxide around. Hydroxide is the most powerful base around, but all of a sudden if an even more powerful base comes along, then hydroxide might itself be attacked by the more powerful base and lose a proton to form oxide. You see? Water is interesting because water is either way. It's equally as good as an acid or base. It doesn't matter. It can go either way with equal ability. And so this would be like right-handed. This would be like totally ambidextrous, you know, or either hand. It's fine, right or left-handed. Well, now we have 3 acids to choose from, and we just look, which one's the strongest acid? We don't even need the chart for this because out of these 3 acids, which one do you think is the strongest? H3PO4. And I don't think we need the chart for this. Out of these 2 bases, which one do you think is stronger? Hydroxide. And so we pick the strongest acid and the strongest base and then react them. Okay, so do that. So the strongest acid, H3PO4, the strongest base, hydroxide. And then we do the reaction transferring 1 proton from the acid to the base. And what forms? Water and H2PO4 minus. Right. In other words, what's this called? Yeah. We call it dihydrogen phosphate. All right, now, just because this is the most likely reaction, it might not occur unless there's a driving force. So let's see, is there a driving force for this reaction? The driving force be?
Yeah, stronger acid to weaker acid. And so what is a stronger acid? It should be this. So I don't know. What would the weaker acid be? Well, if I look at the acid chart and I compare, I look at water versus dihydrogen phosphate. Which one's a stronger acid, water or dihydrogen phosphate? Dihydrogen phosphate's a stronger acid. And so are we going from stronger acid to weaker acid? Does that look right? Yes. Yeah, it looks right because, you know, phosphoric acid is way up here. And dihydrogen phosphate is quite a bit weaker. And so we are going from stronger acid to weaker acid. Right? But is this right? Look okay to you? Does this look okay to you? This is a trick question. It's a trick question because, you know why it's a trick question? Because dihydrogen phosphate is not always an acid. Dihydrogen phosphate is what we call amphoteric. It could go either way. It could gain a proton or it could lose a proton. It's amphoteric. It occurs on both sides of the chart. Do you see dihydrogen phosphate here as an acid? It's also a base. And so how do I know it's an acid or it's a base? How I know it's an acid or base is not by the chart. The only way I know it's an acid or base is because you might always assume hydroxide's a base, but it isn't always a base. It could potentially react as an acid if you react a very powerful base with it. Right? It's the same thing. This is amphoteric, this is amphoteric. So I don't know this is acid or base, this is acid or base. So which of these is the acid, which of these is the base? The only way you can tell which is the acid and which is the base is by looking at the reaction. Because if we were to reverse this reaction and have it go backwards, which one would be the acid going backwards? Right now I have H2PO4 minus labeled as the acid. Is it really the acid? So if we reverse this, does H2PO4 donate a proton to water? Yes? No. No, I have this wrong. The acid is water because water donates the proton to H2PO4 minus to form H3PO4. And so, well, which one's a stronger acid? Phosphoric acid? This is the weaker acid. Do you see that? And so with amphoteric species, assigning the acid or the base depends on the reaction itself, and you have to look at it reaction by reaction. Don't always assume that it's going to be the acid, or it's always going to be the base. Okay? Well, if the acids fall because of the conjugate relationship, this must be a stronger base, this must be a weaker base, and that is correct. And so we look at those. And so we see that there, yes, indeed, is a driving force. Essentially, we would be done here, but we look, you know, if further reaction can take place. And further reaction can take place if there's excess, you know, if excess hydroxide is present. If excess hydroxide is present, then what are we left over with? We re-inventory the solution. We have dihydrogen phosphate, we have water, and we'll have excess hydroxide, additional hydroxide. Can further reaction take place? So we look, dihydrogen phosphate, is that an acid or a base? Well, we just labeled it the base. But when we start over, do we know, is it the acid or the base? We don't know because it depends on what you reacted with. And so it's amphoteric. We reset it. It's acid-base. Water? Acid base, amphoteric hydroxide?
Acid base. Now we define it. We look for the most powerful acid present. Which one's the strongest acid present?
Dihydrogen phosphate.
The strongest acid present. What's the strongest base present?
Hydroxide. And so the reaction will be between these two. So dihydrogen phosphate plus hydroxide gives us what? What we call monohydrogen phosphate and water.
Is there a driving force?
So this is our acid, this is our base.
What's our acid and base on the product side?
The acid's water, that's correct. The base is it. And so are we going from stronger acid to weaker acid? Yes. And so stronger to weaker, we have driving force here.
And so we neutralize the second proton. So we neutralize the first proton, we neutralize the second proton if we have excess hydroxide present.
Well, let's see. If there's still excess hydroxide present, then what we're left over with, re-inventory. Monohydrogen phosphate, water, and some more hydroxide. And so if we got more hydroxide left, then monohydrogen phosphate, acid or base? What is it? We don't know yet, right? And so it's going to be amphoteric. Acid, base, water, the same thing. Hydroxide, the same thing. What's the strongest acid present? Monohydrogen phosphate. What's the strongest base present? Hydroxide. So we end up with this. HPO4 2 minus plus hydroxide gives us what? Phosphate and water. Okay, what's the acid on the left? On the left? Acid on the right is water. So are we going from stronger to weaker? Yes. And so there is a driving force here.
So here we've neutralized the third proton, the acid, and it's favorable.
Okay, if there's still excess hydroxide, what happens? Well, let's look at the solution. We have phosphate, we have water, and we have more hydroxide.
And so if there's still excess hydroxide present, what's going to happen? And so we have phosphate. Phosphate, is it amphoteric? No. Phosphate's got to be a base only.
Water is amphoteric. Hydroxide is amphoteric. And so what's the strongest acid present? Water or hydroxide? The strongest base? Hydroxide. And so what does water and hydroxide produce? Water and hydroxide. So basically NR, right?
And so this is it. This is the end of the line for reaction here.
Would this whole process still apply to sulfuric acid?
Yeah. We do the whole process for sulfuric acid as well. This is that's a good point there, because if we did this process for sulfuric acid, you'd see you would stop a little earlier, you know, not with hydroxide, but with water. We're actually going to do the whole process with sulfuric acid. This is these are chapter 16 style calculations here, but just qualitative. What's that?
Would you write up the reaction side of the water and hydroxide equation? Like, is it ND or?
Oh, NR. Just right, it's going to give us the same thing, hydroxide and water. I wrote NR
There's essentially no reaction because the products are the same thing. There is actually a reaction. There are actually collisions, but since it produces the same thing, it's quote, unquote, NR. All right, we have Bronsted, acid base. Example number 2 here, you can take a look at this. Sodium monohydrogen phosphate, potassium hydrogen sulfate. Try that at home. We have another one, sodium amide and water. You can try this one at home. All right, there's certain things, about this. For example, for sulfide, you memorize. Oh, sulfide, I've memorized that. That's a strong acid. This is not an acid. Strong base. Or it's on the chart. It's a strong, not this chart, but the chart I handed out. It's a strong base, right? And so this way we accumulate knowledge. So, for example, I'm going to talk about this slide in a minute, but when you see something like sodium sulfide, what chemical properties? What are the chemical properties of sodium sulfide? If someone were to ask you, what are the chemical properties of sodium sulfide, what would you say? But one of the things that would stand out, it's got to be a strong base, right? Powerful base, too strong to exist in water. I'd know that. But what else would you know about sodium sulfide? Well, sodium sulfide is going to consist of 2 things. We got sodium ions and sulfide ions. And so let's first start off with, what are the chemical properties of sodium ion? Sodium ion is a common cation in salts, right? But chemical properties are, what does it react with? What does sodium, or what do sodium ions react with? Lots of things? Few things? How would you approach this? Well, this is why I say you want to break chemical reactions into how many types? Into 3 types of reactions, right? And so what we'll do is we'll look at them. Sodium ions, what are the 3 types of reactions? What are its metathesis properties? Well, metathesis properties are, what ions do sodium ions like? Will sodium ions precipitate out with any other anions? What precipitates out sodium ions? Can you think of anything? Nothing. The only way to get sodium and sulfide together is evaporate out water. Otherwise they're apart. Sodium ions and sulfide ions, sulfide asterisk ions, because sulfide doesn't exist right in water. But they're apart. The only way to get them together to form solid sodium sulfide is to evaporate all the water and force them together, right? Otherwise they don't come together, react, and precipitate. And so we're looking for anions that are going to come and react with sodium ions and precipitate. Are there any? No, because sodium, like all group 1, are soluble. There are some unusual anions that will precipitate sodium, but we don't worry about those unusual ones yet. Do sodium ions combine with anything else to form a gas? Like sulfide ions combine with hydrogen ions to form H2S gas. Do we have any gas formation? No. Do sodium ions, are they acidic, basic, or neutral? Are sodium ions good proton donors? Good proton acceptors? No. And so, in other words, sodium ions are unreactive, right, in metathesis. But we don't just have metathesis reactions, we also have acid, base, and redox.
And so if you look for sodium ions in your acid-base chart, are you going to find any? No. No, sodium ions aren't good proton donors. They aren't good proton acceptors. You aren't going to find them on Bronsted. But in addition to Bronsted, we also have to worry about Lewis. We'll talk about Lewis in a little bit later. And so we can consider it, but it turns out sodium ions aren't very good Lewis acids. And so it's unreactive. It's unreactive in metathesis. It's unreactive in acid-base. And that leaves us with redox. And so are sodium ions reactive in redox reactions? And so we need to get familiar with the redox chart. It's on the other side here. When we look at the redox chart, there are two things we have to memorize. And these are the two things that border the chart, the two extremes. One extreme is F2. F2 is called fluorine. What's F minus called? Fluoride. Fluorine and fluoride the same thing? No. Fluorine is very unreactive or very reactive? Unreactive? Okay, I need to adjust your thinking here. Fluorine is extremely reactive. Like, for example, ozone. Is ozone unreactive, stable? Do you like to inhale big gulps of ozone? No, because it would burn and sting. Do you like to drink hydrogen peroxide? No. These are all very reactive. In fact, fluorine is the most reactive. Fluorine chemists have a secret handshake. Do you know what it is? The secret handshake of fluorine chemists. It's like this. The fluorine chemists in retirement like this because they can't do any more chemistry because they've lost all their fingers because fluorine is so reactive, right? And so fluorine is very dangerous. In fact, fluorine, because I worked with fluorine, so when I started working with fluorine, I heard all the horror stories. One of the horror stories is fluorine will catch stainless steel on fire. You don't just burn it in fluorine. Fluorine is much more powerful than oxygen as an oxidizer. Oxygen isn't going to catch stainless steel on fire. It catch steel on fire, not stainless steel. But fluorine will catch the steam. And so I was very worried about fluorine. And so I did some research on this, and it's interesting because I think in the 1950s, the U.S. Army asked for a group of volunteers to walk into a fluorine cloud, holding a bottle and a cap, and go as far into the cloud as they can, and when they couldn't stand it anymore, seal the bottle so they can measure, at what concentrations people can withstand that. And so after I read that report, my mind was a bit more at ease. Maybe it's not going to kill me right away. I can survive in a fluorine cloud. Except, you read the concentrations; they're very small. It's like walking into a cloud of chlorine. It's not. It won't necessarily kill you if the concentrations are low, but if the concentration is very high, it's going to kill you walking in the chlorine cloud. Well, chlorine is a lot less reactive than fluorine, right? And so you need to memorize fluorine. Fluorine we call the most powerful. What? What do we call oxygen? What's one chemical property of oxygen? O2. It's a oxidizer. In fact, the term oxidizer and oxidation came from oxygen, right? But fluorine is much more. You don't need any oxygen. You just burn it in just pure fluorine, and it'll burn much more intensely. Fluorine is much more powerful oxidizer. And so you memorize fluorine as the most powerful oxidizer, and there's a conjugate relationship here because if fluorine's the oxidizer, do you know what fluoride is? What we call that? It's conjugate reducer. And so if fluorine is very powerful, fluoride is very weak. It's a very weak reducer. You know what reducers do? Oxidizers take electrons, reducers give up electrons. And so fluoride doesn't want to give up electrons. It holds on to the electrons very tightly and doesn't give up. You might think of fluoride as being reactive, right? Fluoride is reactive in metathesis reactions, but in redox reactions, fluoride is not reactive. Right? Metathesis reactions would be like bone and teeth. You know, fluoride is very dangerous for bone, potentially dangerous for bone and teeth because it's a metathesis. But we're talking redox now, and it's different. What's the most powerful reducer on the chart? Lithium. Lithium is the most powerful reducer on this chart, which means it's the species that's most likely to give up electrons. If lithium is the most powerful reducer, then its conjugate, lithium ion, is the weakest oxidizer. Because lithium ion doesn't really want electrons. If lithium ion doesn't really want electrons, then lithium can easily give them up, right? But this is really weird because if you look at it, you know, the metals should be reducers. The metals are what we call electron rich. They can give up electrons easily. And so sodium is a pretty good reducer. In fact, it's a very powerful reducer. And then potassium is even more powerful. Right? Sodium versus potassium. Potassium's better, right? Lithium is a kind of odd here. Do you know why lithium is a little bit odd here? It's out of place. Because when we think about reducing ability, we usually think about ionization energy. And so potassium has a lower ionization energy than sodium because, why? Potassium's ionization energy is lower than sodium's ionization energy because it's larger, right? Potassium is larger. Potassium being larger, it's easier to pluck an electron off a big atom than it is off a small atom, right? What's weird here is we're going to lithium. Lithium's ionization energy is actually quite high because lithium is very small. And so this is very odd because lithium has a high ionization energy, much higher than potassium's, and yet it more readily gives up an electron. Why? It's not electron affinity. It's not half-filled orbital. It's not that. We don't get a half-filled orbital. It's because we don't look at just one factor. We look at, not only do we look at the reactivity of the reactant, we also look at the stability of the product. And the more stable the product is, the more that's going to drive the reaction. And so it turns out that we have Li plus AQ is a lot more stable than K plus AQ. Do you know why? Li plus AQ is a lot more stable than K plus AQ because of its small size. Do you guys know what Li plus AQ do you guys remember hydration and solvation from chapter 13? Hydration and solvation. In chapter 13, lithium ions, these are going to be surrounded or hydrated by water molecules. And those hydrated ions, lithium ions, are going to be more stable than hydrated potassium ions. Potassiums are bigger, lithiums are smaller. And so you have what we call ion dipole attraction. You have the ion charge being attracted to the dipole of water. And you know, these electrical attractions depend on two things. What do they depend on? Magnitude of charge and the size, right? The higher the charge, the smaller the size, the more the attraction. And so both of these have the same charge. Lithium has a smaller size, so it's going to have stronger ion dipole attractions with the hydrating water molecules. Go back to chapter 13 and look that up for me. And so this is really weird because potassium reacts violently. You get and when I was at UCSB, somebody got a 200-gram stick of potassium, like this big, threw it into the faculty swimming pool there. Big explosion, 20 to 30-foot plume of water shooting up and big flash of red, orange light. It was pretty intense. and a loud noise, big bang. But if you did the same thing with lithium, you just get a mild reaction. You know? And so what happens is, yes, potassium initially reacts much more violently because it's a lot easier to pull the electron off, but it doesn't release as much energy because the hydrated ions aren't as stable. Whereas lithium reacts slower. You know, it's harder to pull the electron off, so it reacts slower. But even though it's slower, in the long run, it releases more energy thermodynamically because the product is more stable. And so this is slower, but you get more yield. This is faster and more violent, but you get a little bit less yield in terms of energy. And then we have something like cesium. You know, cesium, what would you expect cesium to be? A better or worse than potassium? Cesium, it turns out to be better. You know, more violent. I mean, there are two factors here. Both potassium ions and cesium plus ions are big, so it doesn't really matter. They're both big. It's not going to be that stable. You know, these are unusually small, so it's quite stable. And so we're really looking at the ionization energy. Cesium, is it bigger than potassium or smaller than potassium? A lot bigger, so it's a lot easier to ionize, and therefore it's going to be much more violent. So cesium would be the most violent out of all these. Cesium is quite dangerous too because it has a very low melting point. You know, what reacts more quickly, solids or liquids? Liquids, you know, there's more mobility. Solids have very limited mobility. And so cesium melts, you can melt it in the palm of your hand. You'd never put solid cesium in your hand because it would react violently with your skin. But if you had a vial of it or an ampule of it, you know, in a sealed glass container, it would melt sitting on your hand. And so it's very dangerous, and sodium is very dangerous too because, you know, I was working with some sodium in the lab. I took some sodium metal. Sodium metal is a powerful reducer, and I was reacting this with alcohol. And normally when you have a potentially violent reaction, you have an ice bath, you know, to cool it down in case, and temperature impacts the speed of the reaction. And so the colder the temperature is, the slower it's going to react. But I couldn't have an ice bath because what do you think sodium will do to water? Have you ever seen sodium and water react? Yeah? Actually, there's a video here, but there's no sound, unfortunately. So I'll just play the first part. Have you seen this? Disposal of surplus sodium. This is the Army disposed of some excess sodium here in these 50-gallon drums, I think, or even bigger than 50 gallons, let's say. These giant drums of sodium. Just let them roll into this lake, this frozen lake. Dips through it. You really need to see the sound, and too bad this wasn't in color, so you could see all the light that was generated from this. But that's, you know, that's what the potassium looked like on a small scale. It was pretty intense. And so take a look at this. This is just on YouTube, but that's a gigantic cloud, by the way. It's hard to tell what the scale is until you actually see. Well, actually, I guess you could see there's a person standing there. All right, so that's sodium reacting with water. Water is not very reactive, but sodium is quite reactive. And so anyway, I couldn't put an ice bath there because if the sodium came into contact with water, I'm going to expect a fire. Right? And so didn't have an ice bath, and I should have gotten something else like a dry ice acetone bath or something. But I had to do this in something called a dry box. In a dry box, there's no water and there's no oxygen, because the oxygen will react with the sodium too. And so all I could do was I put a big plate of aluminum in there and hope that cooled it enough. And so what I had was I had these big chunks of sodium floating in my alcohol, and I started crushing them up. But as I was crushing them up, it started to react, and as it started to react, it's an exothermic reaction, so that the temperature started to climb. As the temperature was climbing, I put it on the aluminum plate, but it wasn't cooling down fast enough. And then all of a sudden, it went exponential.
and it just shot up. The sodium melted and it exploded immediately. Fortunately, it exploded in the dry box, so there wasn't any damage. But it was very loud, and a lot of people came running down to see if I was okay. It was okay. But yeah, that's my experience. And so these guys are very violent, and you should know that. Violent, strong reducers, strong oxidizers. But sodium ion is very different than sodium metal. Right? Sodium ion is very unreactive. Sodium metal, very reactive. What about sulfide, though? And so sulfide, sodium ion actually is here. So sodium metal, very reactive. Its conjugate is very weak. And so sodium ion would be a weak oxidizer. And so in other words, sodium ion really doesn't participate in any metathesis. It doesn't participate in any acid base, and it is a very weak oxidizer. So sodium ion is very unreactive in terms of those three. But actually, was it sodium? I guess it was potassium we were looking at. Sorry, it was supposed to be potassium, but it's potassium ion is the same thing, right? Sodium ion. Very unreactive. Now, potassium ions in biology, you have the sodium channels, potassium channels. There you could see something, the balance in ions. It's different. What about sulfide? What comes to mind with sulfide? In terms of the three chemical properties, we look at metathesis. What types of metathesis reactions does sulfide undergo? Well, will it precipitate with anything? What cations does sulfide like, if any? Not group 2. It doesn't really like group 2 or group 1 or ammonium, but it likes everything else. In other words, sulfides are all insoluble except for group 1, group 2, and ammonium. And so if I had iron 3, it'd react. Copper 2 would react. Copper 1 react. Anything. And so it's very reactive in metathesis. Correct? Lots of cations sulfide likes. What about acid base? It's very reactive in acid base, right? Sulfide is a powerful base. What about redox, though? What can you say about redox? And so when we look at this chart, sulfide doesn't occur on this chart, but we have a more comprehensive chart. And the more comprehensive chart is in our textbook in Appendix D. And so let me go to this. Mastering Chem is nice. Are you guys familiar with Mastering Chem? Okay, I haven't set it up yet. I need to set it up, but there are quizzes here that you can test yourself, some review things, and some additional practice problems. You aren't going to get any grade from Mastering Chem, though. But they have the e-text there. And so if I go to the appendices, I have Appendix A, B, C. We go to Appendix D. Appendix D, we have the electron configurations, some thermodynamic data, equilibrium constants, which we'll talk about later, and redox. And so we have a more comprehensive redox table here. And you can see it starts off with fluorine here, but there are a lot more species here. And so what would you expect sulfide to be? An oxidizer or a reducer? Now oxidizers want electrons. So oxidizers, one characteristic of those are they're electron poor. They want more electrons. Reducers typically are electron rich. They have electrons that they can lose. And so when you look at sulfide, would you consider that electron poor or electron rich? Electron poor, so it wants more electrons. So maybe a 3- charge or a 4- charge would be good for sulfide. What do you think? Or maybe it's just happy as is. Sulfide has gained 2 electrons. So it's isoelectronic with argon. Does it want to gain more electrons? No. And so it doesn't want more electrons. If it wanted more electrons, we'd consider it an oxidizer. And so the only thing it has potential to do is to lose electrons. Okay? And so it's likely to be a reducer. And so we take a look at the chart and see here if we can find sulfide on the chart. And so let's start off with the strongest reducer. The strongest reducer should be lithium. And so we got lithium, and then we got all the metals. You see all these are metals here. Let's continue. Zinc metal, solid acid, some others. Doesn't look like we see any sulfide there. Although here we have something close. This is hydrogen sulfide. And do you know oxidation states? What's the oxidation state of hydrogen? You know, hydrogen sulfide, +1. What's the oxidation state of sulfur? -2. So do you see this is like sulfide, hydrogen sulfide, right? And so in this case, it's going to be behaving similarly because H2S is going to produce sulfur. And so the sulfur loses 2 electrons. Sulfide loses 2 electrons to go to sulfur. What happens to hydrogen? Hydrogen goes from +1 to +1. So nothing happens to hydrogen. And so what we see is the sulfide in hydrogen sulfide is a reducing agent. It loses the 2 electrons here. And so even though sulfide's not here, sulfide should be comparable to hydrogen sulfide, which is a moderate reducer in terms. And so as far as redox goes, sulfide should be a moderate reducer. Does that make sense? Now, some things don't appear on the chart. So for example, oxide. What should oxide be? Well, oxide is likely to be a reducer. Will oxide be a better reducer or a worse reducer than sulfide? A worse. Why? Because it's smaller. A smaller species is going to be harder to pull the electrons off, right? And so oxide is going to be worse. What about telluride? Better. Telluride should be better than oxide. Will it be better than sulfide? Yeah, because it's bigger. Telluride's bigger, so it's easier to pluck electrons off. How about selenide? Somewhere between, right? It's got to be between sulfide and telluride. And so, everything doesn't have to appear on the chart, right? Because we use the 2-pronged approach. We use a mix of just factual knowledge, this kind of memorization or looking it up in the chart type of thing. And we use a little bit of theoretical knowledge. Theoretical knowledge is we know how the size changes, in the periodic table. And that type of stuff we review. How late do we go till today? 12:40? Okay. I was going a little bit slow, so I missed it one.